is on fire. So if you guys are familiar with El Moro,
What was it?
El Moro, are you familiar with that park down on PCH?
Like by Laguna, kind of.
Yeah,
There's a fire over there right now.
yeah. So, and I know exactly where it is too. So if you go into the park, I don't know, I'm seeing embers outside. Yeah, if you go into the park, the fire is south of that. So if you went into the park, like into the parking lot, and then you took the trail called BFI to take you up to the southern part of the Morro Ridge, all of that to the right, down towards the houses, is what's burning. So here is the answer. I'm smart. I will buy your house. I will make it quick. I'll give you cash, no headaches. Call me now. 844-86. All right, changing gears here. We're going to develop something new. Now, this really isn't a technique of integration. It's more of a algebra result. So this is section 7.4. And it's partial fraction decomposition. Okay, so if you've had a class with me before, you've heard me say this a few times, that polynomials with real coefficients, they behave very similarly to integers. Meaning if you have a concept with integers, there should probably be a corresponding concept with polynomials. So the kind of thing that we're going to want to do would be to integrate something like this. Like, let's say we had an x minus 2 and an x plus 3. The question here is, can we find numbers a and b, which are just going to be numbers, such that 1 over x minus 2 times x plus 3 like so. Trams are coming back to Disneyland. And realize trams didn't run away. Okay, so if we could, then integrating this thing would be real easy, right? Because it'd just be a times the log of x minus 2 plus b times the log of the other one. Right. All right, well, see if we can get some justification for some of this stuff. So let's go to integers. And let's suppose that I had 1/6, which is 2 times 3. And I want to write this as a over 2 plus b over 3. Well, the way you would find this is you would cross multiply and get 1 equaling 3a plus 2b. So I think you just let a equal 1, b be negative 1, and we've got it. What about 1 over 12? One way we could think about 12 is 3 times 4. Can we write this as a over 3 plus b over 4?
A is 1, B is negative 1.
Yeah, let's see. We'll just cross multiply the guy, right? And say 1 would equal 4a plus 3b. So again, looks like a is 1, b is a negative 1. So this looks like it's working, right? But what if I was to write 12 as 2 times 6? Cross multiply, and 1 is going to equal 6a plus 2b. Okay, now we're trying to find integer solutions to this, right? A and B. Anybody want to venture a stab as to why you can't find an A and B to make this work? You're going to see as soon as I write it down, you're going to go, oh, okay, oh shit. All right, ready? Okay. Does that look weird to you? That's an odd number. And no matter what you pick for A and B, that would be even, right? So, no solution in at least the integers. Okay, so let's compare these three things. Yeah, that's right. That's some when I do like just a big loop of the park. I would start at Ridge Park and I go down to the parking lot and then I go climb up BFI, and that's right where that fire is. Not that I was thinking about going riding today. I kind of retired from mountain biking. Anyway,
What path? Well, my bad. I was wondering, like, what paths do you take when you mountain bike?
and what trails do I ride out there?
Yeah, like, do you usually go on the mountain hills, or is it just like regular, like a street way?
No, so I out in Laguna, in El Moro / Laguna Wilderness. There's all kinds of trails. There's fire roads, single tracks. Of course, that area is all going to be closed for 2 weeks until they knock that fire down. But there is a trail right where that thing is burning, which is called Beer Stop. I've been. The bottom of it is right where those houses. So where they're showing this burning stuff, if you take the so there's a trail that goes through the second canyon that dead ends at all these big green fences where these tennis courts are, and that is the rich Laguna people. And the Rads guys have made a trail called Beer Stop that they usually go down it, but you can climb it. Well, you have to walk your bike up. But anyways, it puts you right back up at the top of where BFI is. And then a little ways down further, there's another one that I've actually ridden This thing is dangerous as shit. You look it up on YouTube. It's called Burnt Stump. And there's this one section, because everybody GoPros it, you don't really get the steepness of it. There's other trails on the other side of the freeway in Laguna, like, you know, Telonics and PG. PG's is that's the one where, I mean, there's been some people that have gotten some serious injuries and flown out of there by helicopters. Anyways, these two numbers right here are prime. Okay, so maybe that has something to do with it. But these two numbers aren't prime. Well, 3's prime, 4 isn't. Okay. But the thing that they have in common with the pair above them is that they don't have any common factors. When two numbers don't have any common factors, we say they're relatively prime. Okay, so the reason I guess that it doesn't work with the 2 and the 6 is because 2 and 6 have a common factor of 2. Okay, so the big result from number theory, this goes clear back to Euclid. This is a number theory thing. That said, if A and B are relatively prime integers, there exists integers x and y, which are integers, such that we can always make a 1 out of A and B. Okay, so now this is a huge thing in ring theory. Like, if you have two elements that you know you can make 1, and this happens because this concept of prime then generalizes, like we're going to generalize it right now. Okay. Okay, so notice that if we were to divide everything by A times B here, if I did AB, this would lead to X over B plus Y over A equaling 1 over A times B. Okay. All right, so similar result now for polynomials. If I have two polynomials, AX plus B, linear polynomials, and CX plus D are, if these guys are relatively prime, then there exists real numbers A and B such that if I had 1 over AX plus B, now most of the time it's going to be, the, starting with the 1, like X plus 2 times X minus 3. But anyways, CX plus D, A over AX plus B plus B over CX plus D. Okay, now there's more to this story. Back up in the number theory result, the A and the B are always going to be in magnitude smaller than these two numbers. Okay. And again, this is just, it all comes from a consequence of something called the division algorithm. So none of you guys are math majors, but maybe one or two of you might minor in it. And should you minor in math, you know, you might take abstract algebra or number theory. Learn a little bit about this. Okay, so in polynomial world, the thing that measures size is the degree. So the degree of a ax plus b, that's a degree 1 polynomial. Whereas numbers are degree 0 polynomials. Okay. Now just hang with me here. There's more coming with this story. So what is really going on here is that those numerators, A and B, what they actually are the possible remainders that you could get upon dividing ax plus b into some kind of polynomial. You guys remember this from you know, your days back in grade school. You know, if you did a division problem where you did 17 into 43,900 and 262, you know, you're going to get some quotient up here. And then eventually there's going to be a remainder, right? And the remainder has to be less than 17. Remember that? Kinda?
Yep.
Okay. So in the world of polynomials, if you were going to take an ax plus b and divide it into some kind of a polynomial, you would get a quotient. And then down here, you would get a remainder where the degree of r of x has to be smaller than the degree of ax plus b. But that's 1. So this means the degree of r of x is 0. So that means it's just a number. Okay. Now, all calculus textbooks talk about this. This is always a section in every calculus textbook. And I get sent lots of calculus textbooks for free. You know, they want me to review them and whatever. And anytime I see a new one, I always go straight to this section. And I like to see how they handle this, because there is a lot of explanation, I think, that you guys deserve. And this is what I spend this part of the lecture on. We're not going to do very much calculus for the rest of the next 20 minutes or whatever until we hang up. But it's going to be explaining why this works. Because if I needed to now integrate this, you know, we would just integrate each one of these things and get a couple logarithms. Okay, so the justification of all of this stuff is something called the Chinese. Is that how you spell Chinese?
That's correct.
The Chinese remainder theorem. Okay. Now, the reason this result is called the Chinese remainder theorem is because the first place that noted in history where this thing was written down somewhere, the oldest, is on some piece of parchment that was discovered somewhere in China. That's why it's called the Chinese remainder theorem. And it has something to do with like modular arithmetic. So what do I mean by that? So think about clock arithmetic. You know, what's 12 o'clock plus 14 o'clock? What would your answer to that be? 14.
2 o'clock.
Yeah, so you take, what did I say? 12 plus 14. So that's
Yeah.
20, that's 26 o'clock, right? But then you basically mod out by all multiples of 12, and whatever is left, the remainder would be the answer, right? So this works nicely like if you're military time, because if, you know, everything is on 24s, we don't have to reset at 12, but it can still work with 12. We take 8 o'clock plus 8 o'clock, that's 16 o'clock. So that translates to 4 o'clock, right? Okay, so now the Chinese remainder theorem is not talking about o'clocks. I'm just saying that it has something to do with this kind of arithmetic. Yeah, and you can, guys, right now on your phone, if you want, look it up on Wikipedia. It would be right there for you. And it's not going to look anything like what we're talking about. Okay, so what happens then later on, like in an abstract algebra class, we look at this Chinese remainder theorem, and then we apply it to various other different structures. And the structure that we're looking at is like polynomials, the polynomial ring. Okay, so with this in mind, if we were to take a quadratic ax squared plus bx plus c and divide it into a polynomial, we would get some kind of a quotient up here, right? And the remainder down here would be smaller than this guy. So the remainder in its most general form would look like ax plus b. Okay. Okay. So we need to identify what are prime polynomials. Polynomials that cannot be factored into smaller polynomials. So like, for example, x, or for that matter, x minus 1, or for that matter, ax plus b. Okay, now we can factor x. You've seen me do these dirty, sneaky tricks before, some of you in Calc 1, where we had to figure out limits. But those two things don't count as polynomials. Okay. So these linear guys are prime. And we also have certain quadratics that are prime, meaning that they can't be factored down any further. Do we have a characterization about this?
Quadratic.
Right, so a quadratic could either have real roots or no real roots, right? Or maybe one exact real root. Okay. Now remember, from your days of pre-calculus, if P of A in a polynomial is 0, then that means that X minus A is a factor. So we can't factor this down into smaller linear polynomials when this discriminant is negative. Okay. This is now the end of the list. Now, there are plenty of polynomials that are relatively prime to each other. Okay. But as far as just being prime, like for example, most of you would probably think that this guy is prime because it doesn't have any real roots, right? No number to the fourth power is -1 unless you start using complex numbers. But I want you to go ahead and verify this. Now, sometimes in pre-calculus, I give this as an extra credit problem. And I say, I'll give you 1 point if you can factor it. Now, once we get back into the swing of things, I was laying there in bed at 8 o'clock today thinking, do I really want to go over there? I'm just going to be all by myself in that class bored. At least, you know, if you guys were there, I have somebody to talk to. I mean, I'm going over there today. There's a game at 2. If you guys want to ask me questions, I'll be over at the ballpark at sometime around 2. I usually show up in like the 2nd or 3rd inning.
Were you there on Tuesday?
Yes, I was there.
Really? I came over after my practice with my teammates and I didn't see you.
After track practice?
Volleyball.
Oh, volleyball. Let's see. Yeah, we're playing Saddleback, or we're playing Palomar. And I got there. The game started at 12. I didn't get there till like 2:30. And then I had to be somewhere at 3. I usually, any home game, I'm usually there for a few innings or so. So I'll be there today, probably a little longer.
Cool.
Professor.
Yep.
You know, I think about the basketball games. My friend was like trying to figure it out, and then he said that they weren't allowing people in the crowds right now.
Well, that's not the case at the baseball field. No one's wearing the mask.
Yeah, they don't
When-
have spectators at the men's volleyball games either.
Probably because it's inside, I guess.
Yeah, I guess.
No, so our first home game this year was against El Camino as part of this Memorial Cup in memory of Altabelli and another player that died at El Camino. And it was the renaming of the park to the John Altabelli Park. And there was a big crowd there, including President Suarez, everybody hugging and good to see you. And of course, not a person had a mask on, including Suarez herself. So if you guys are like in class and you're half masking and stuff, I'm not gonna say anything, but there might be some of your neighbors next to you that might be bugged. So this is gonna be a real shit show. Because, I mean, there are faculty members that I personally know that are germaphobes. That they already, before any of this shit, couldn't wait till the class before them got out and everybody left so they could go in and sanitize everything. And this is before COVID, you know. All right. So the point is that due to the fact that if you were to take any complex number, a plus bi, and multiply by its conjugate, a minus bi, you get a real number. And so this is the actual extra credit portion of it. It's like, explain why this is always the case. Okay, so for you guys, I'm just telling you, we're just trying to get this stuff to use it for some calculus. So if I had, let's say, for example, an irreducible quadratic in the denominator. So let's say I had something like x plus 2, and then something like x squared plus 4. When we would do the partial fraction decomposition here, we are going to get the possible type of remainder you could get by dividing a polynomial by x plus 2. And then what goes up here is what is the most general type of remainder you could get if you divided a polynomial by x squared plus 4. Okay, now of course, if we allow for complex roots, then we can just use i's, and sometimes to find a, b, and c, you resort to that stuff. Okay, now this portion of this doesn't have an analog in the integers because when the polynomial structure is a little bit, well, it's considerably more rich. There's more going on there. The set of integers as a group or as a ring can be generated by one number and one number at all. Whereas we need lots of things for real polynomials. We would need a 1 to get all the numbers, but we would also need an x, and we would also need an x squared, and so on and so forth. Okay, now again, textbooks generally don't give you any kind of an explanation as to why this works. Okay. This explanation, depending on what semester it is, and I can't see any of your faces, even though I've got 2 devices going. It's just showing my screen being shared.
Professor, I have a question.
Yeah.
What are those, the diamond within the 1 represent?
Oh, what it means is it's a cyclic group generated by 1. Like, you can get any integer by adding n up, by adding 1 up enough times.
What was
That's
it
all.
called again? Cyclic?
Cyclic. It's an infinite group. A group is another thing. We're kind of getting off topic here. Okay, well, anyways, let's say that we were trying to integrate this last thing I wrote down. Well, we would then just say this would be a times the log of x plus 2. And then we would separate this up into this piece, right? And then that would be a u substitution. This would be some kind of a tan inverse, right? That we would do. Okay. Now, another part of this piece is when we have repeated factors. Okay, so if I have something like this, where I have repeated irreducible factors. Now, this is where you really need the Chinese remainder theorem to see how this separates up. And again, you guys are, I mean, you would have to take several math courses beyond calculus until you're ready for the Chinese remainder theorem, at least 3. Most of us don't see the Chinese remainder theorem until we get to grad school. If you're at a high-powered place like Princeton or Berkeley, you know, UCLA is pretty high-powered. The undergrads there, as long as their grade point average remains high enough, they let the undergrads take the graduate courses if they're like abstract algebra. You can take that as a graduate student, you know, with all of us graduate students. There was like a bunch of people that were doing that. I tell you who was doing that. You guys watch that show, The Wonder Years? It's got Don Shield as the main voice. You guys know that show I'm talking about? The Wonder Years? Well, when I was in high school, this is a reboot of the old Wonder Years, and the main girl in the show, Winnie, when I was at UCLA, she was an undergrad, and she, CX plus D. And then we have to include another one for this piece. So these things get to be real shitty. Okay. Now, as far as like what to do for the exercises and all this stuff, this is really more of an algebra topic than anything else. So on Tuesday, when we're all back together in the big room, my big plan will be to be broadcasting on this thing, but walking around with this is not such a good idea. And so I think what I'll do is I will, I'll have my mini going, and then if I'm doing something on the board, I'll just turn the camera around on the mini and, like, you know, I'll take over the host job, and then I'll just point to the camera, and you guys will tell me, yeah, I can see it. Because I'll try to do everything on the iPad, but it's inevitable I'll eventually write something on the board. Okay, well, 7.4, you know, is just a ton of integrals to do. But, you know, get in there with the partial fraction stuff. Now, when we go to take the test, I try to arrange all these problems so that they work out all nice you know, like the A is 1 and the B is 1. Sometimes I get a little crazy, especially like with the over x squared plus something. I usually like to have the A equal 2. You know, that way if U is x squared plus 4, then the du is going to be that 2x dx, you know, thing in the top. Basically what I do is I start with the answer and then I take the derivative. So if I want the answer to be tan inverse of x plus the natural log of x plus 1 over x, I take that derivative and then I common denominator it. So on the test, it looks uglier than shit. But when you do the partial fractions on it, it all works out to where A, B, C's, they're all nice numbers. Okay. All right, so this, I guess, officially marks the end of our required this kind of stuff. Now, I'd be willing to bet there'll be a day or two this semester where I cancel class because I'm not feeling good, and I'll just, in that case, email everybody and say, everybody be on Canvas or on Zoom today because I might, you know, be sick or something. We're really being urged to, if you don't feel well, don't come to school. I never would waste a sick day on being sick. You know, if I had a raging case of the flu, I'd be in there. You know, I take my sick days on for fun stuff, you know, like going to Vegas and shit like that. But now we're being strongly encouraged, you know, to do that. Okay, well, what we're going to be doing next week is a whole bunch more of this stuff. Our first 3 weeks are pretty much spent integrated. So there's more tricks that we're going to be learning. But once we get to the end of next week, that's probably going to be the end of all of the tricks, you know, and then we move into other things. Okay. But that still doesn't mean you shouldn't be integrating. All right. Feel free to email me over the weekend if you have any questions about.
I have a question.
Yeah.
How far in the textbook homework should we do? Do you think should be best?
Well, right now we're through section 7.4. And the standing assignment is just do the integrals. The reason I'm bringing up baseball games is because baseball season is the best time to do math. You turn on a boring ass baseball game and you sit there and you do problems until the game's over. Now there's no baseball. I mean, I bet you could find something on somewhere. Or you can just go over to OCC, sit in the bleachers. There's only a couple dozen of us over there. You know, and take your math book. And if you run into a problem, hey, you might just see me and I may be able to do that. A couple of the football players figured this out a couple of years ago. I had them for pre-calc and then calc 1. It was the running back and one of the linebackers. And they knew I was always over at the field. And so they're in the off season. So they would just be lifting. And then they would meander over. Oh, fancy seeing you here. Hey, since I've got you here, can you show me how to do, you know? So that's fine. It doesn't bug me. All right, guys. That's it for today. See you on campus, maybe in person on Tuesday.